Okay. So, hello and welcome to this Institutional Mechanical Engineers technical lecture titled Swimming Microrobots for Biomedical Applications. Here, we will explore structures that freely move inside the human body and reach currently inaccessible areas to perform delicate biomedical operations such as diagnosis, surgery, cell transportation, and localized drug delivery. Application of these microrobots will revolutionize medicine and have a high impact on society. In this event, theoretical and experimental results and challenges facing application of microrobots in biomedicine will also be discussed. So this webinar is being recorded and it will be made available later through the IMechE YouTube channel. You may also contact us to request the slides as well. I am Murat Islam, a member of the IMechE Lancashire Area Committee, and I will be managing this 1 hour long webinar. We will have about 10-15 minutes Q&A session at the end, so please use the chat to submit your questions, and I'll endeavor to direct them to our speaker later. Our speaker, Dr. Ali Gambari, graduated with a PhD degree in mechanical engineering with a focus on microrobots from American University of Technology in 2011. He was a postdoctoral research fellow in biometrics laboratory at robotics engineering department at Daegu Gyeongbuk Institute of Science and Technology. Apologies for the pronunciation there. And he is a guest researcher in multiscale robotics lab at ETC Zurich. He also worked as an assistant professor at Tufts University and as a research fellow at the University of Leeds. Currently, he's a lecturer in mechanical engineering in the School of Engineering at the University of Central Lancashire. Ladies and gentlemen, our speaker for this lecture, Dr. Ali Gambari. Thank you. You can take it from here, Ali. Thank you.
Thank you, Murat, for the introduction. So let's start our talk. So I'm going to talk about microrobotics and what is about the applications and as well some challenges that and my research. So when we say small scale robotics, we talk about a wide variety of devices ranging from millimeter size down to mobile or autonomous devices with a nanometer size. Microrobotics covers an area for the devices with a dimension less than 1 millimeter. So the area of the microrobotics works about is from millimeter to micrometer. So we usually get devices. So we have several developed devices like a Helical Microbot, more in these Helical Flagella, and other microbots. But I'm gonna show a video here. This video shows some parts of a movie made by Hollywood in 1960s, and it showed that thinking small, it's not new. So in Fantastic Voyage, the movie, the crew and scientists and their submarine are miniaturized using a top secret technology to enter the bloodstream of a dying man to save his life. You know why? Top secret technology, because nobody knew it. So that's the problem. So the Hollywood could make the movie, but they haven't thought about. They didn't have to think about how to make the device but. That's an interesting movie, but the problem is if even in that amazing miniaturization technique would exist, so it wouldn't work at micro scale. So the submarine propellers, they wouldn't have function in micro scale at that scale. So we need to think a bit different. So we need to rethink of our approaches and methodologies we use at macro scale. So what's the problem? So scaling effect is an important effect when we compare microscale with macroscopic. Still, in macro robotics world, physical laws, we have the same physical laws as macroscopic world. But what is important is the relative importance of physical laws. So we know volume scales as L cubed, it's proportional to L cubed, but surface scales as L squared. So this difference between volume and surface is the major challenge in macro scale. So we have a ratio between surface and what is related to surface, I mean surface forces to volume forces. So the ratio of surface to volume is proportional to L to the minus 1. What does it mean? So it means when we scale down as a system, a device, like 1,000 times, so the surface forces scales down by 10 to the minus 6, but volume forces, they scale down by 10 to the minus 9. So the difference between volume and surface effects leads to many scaling issues when we talk about the microscopic world or microrobotics. So we need to rethink. So our intuition about the swimming techniques or swimming methodologies or flying methods at a macro scale, they don't work at micro scale. So we need to think um, different approaches. So, but okay, so let's talk about the physics. So we get low Reynolds number flow in microscopic world. So the Reynolds number, usually we use Reynolds number to explain the fluid regime. So when it's low, it means that inertial forces are negligible compared to viscous forces. So it's when we have a low velocity or higher viscosity of the fluid, or when we have very small sizes, so the Reynolds will be so small. So in case of a human swimmer, so we will have a Reynolds of 10 to the 4 to the power of 4, but for the microorganisms or microrobots, we get a Reynolds number of 10 to the minus 4. So there is a big difference here. So in micro scale, we get Stokes equation. They govern the regime, the flow regime in micro scale. So you see here the Stokes equation, which is derived, I mean, is a simple case of Navier-Stokes equation. So we haven't got any parameter here dependent on time. So there is no time dependence in this equation. So it means that when we have a reciprocal motion, so simply back and forth motion, we wouldn't get any net propulsion for that motion. So we need to use drag-based swimming methodologies in micro scale. But yeah, so in this slide, so we have also we compare the Reynolds, the regime of the high Reynolds and the low Reynolds. So you see here we have a ball, and when we remove the ball, still it continues its motion because we have inertia. But at micro scale, when Reynolds is very smaller than 1, so when you lift the force, so it stops immediately. So we can't use inertia based like what we have in fish and in like submarines. So, but already we have I mean, nature has solved this problem. So there are bacteria and microorganisms that we can get inspiration from the nature. So you see here we have got a Paramecium. So Paramecium is covered with several cilia. There are like hair-like appendages cover the body of this Paramecium. So they beat against the water when they move in an effective stroke or power stroke. They are straight and then they beat against the water. But when they want to come back during the recovery stroke, they get bold to have minimal effect on the fluid. So that's why we haven't got asymmetric motion for the cilia here. So we can have a net propulsion for the microorganism. In the middle, we have got a eukaryotic flagella. So they have soft flagella using wave traveling through the tail of the sperm, so it can swim in the water. So there is some motors inside the body, so it generates a wave through the tail and it can swim in the water. And we have got prokaryotic flagella. So they are almost rigid flagella. They rotate and produce the propulsion for the for the bacteria. So as you see in the video as well, they are recorded by Howard Berg in Harvard University in 1970s. He could record this video and look at the he looked at bacteria and saw that they have got a motor. So that's maybe the only motor in the nature. So we have got a molecular motor for this bacteria, which can rotate the helix and the helical tail and generate a propulsion for the bacteria. And based on these, bacteria and microorganisms, there are bio-inspired microbots in literature. So in 2011, I proposed ciliary microbot, an idea of the ciliary microbot. We developed the idea and developed the equations of motion and dynamic modeling, and we could prove that the microbot will have a net propulsion, and we evaluated the efficiency of the microbot. In 2006, eukaryotic flagella motion was proposed for a microbot, and as well there are several helical microbots. First one developed in 2009 by the Brad Nelson group in ETH. So these are all based on what we have in nature, so all bio-inspired microrobots. For the helical microrobots, we can relate the velocity to the torque and the force applied on the microrobot. So if there is a magnetic field, for example, from outside, it can generate magnetic field and rotation in the helical microrobot. And it can have a linear velocity. You see here in the plot. So the vertical axis shows velocity, which is the linear velocity of the microbot, and the horizontal axis shows the rotating frequency. So at a certain frequency, which is called the cutoff frequency, the velocity of the microrobot drops. So when we increase the rotating frequency of the helical microbot, the velocity increases up to a certain amount, but then decrease. So this is called the cutoff frequency. And here I've got some videos of helical microbots. So you see here the microbot moves. So this microbot is 100 micrometer in length and is actuated by an external magnetic field. We could manipulate the microbot and change the direction as well using the magnetic field. And here also I have got video of a microbot. So a helical microbot taken by a fluorescent microscope. So these microbots are in the scale of like 100 micrometer in length, but we could, using 3D lithography method, we could make microbots in the scale of 10 micrometers even long. So let me see how we can. Okay. So I'm using my pen as a laser pointer, so I can't. So okay. So let's see this video, which is a helical microbot, but it has a function to catch and release, a bead. So it rotates when we have a rotational magnetic field. It rotates and move in the fluid. But when we we reverse the direction of the magnetic field rotation, so it can release the bead. So it can catch the bead and move to a place, and then using the reversal motion of the rotation of the magnetic field, it can release the bead. And for the fabrication of these 3D structures, we could use a 3D lithography machine. So in this method, two laser beams are focused on us to make an ellipsoidal spot, which acts as a building unit, and with precise control of a piezoelectric driven stage, we could control and scan pre-programmed or pre-defined structure in the photoresist. And then after exposure, so some parts are exposed, but some we could develop the structure by removing those unexposed photoresist. So we could develop and build a 3D structure. And the thickness that we can make these helical microbots that is down is the machine is capable of making 1 micrometer size lines of the helical microbot, and we could do several thousands of microbot on a wafer. So they are batch fabricated. The scanning time is a bit long, but at the same time you can fabricate several thousand of the microbot. So that we have, the microbots can have different biomedical applications. So they can be used for monitoring, can be used for targeted therapy, surgery, and tissue regeneration. For monitoring, they can be used as imaging. So these smart pills, sensing, sampling, and marking for targeted therapy. They can use to deliver locally, to deliver locally the drug, the medicine. Can be used for hyperthermia, brachytherapy, and can be used to transport cells like stem cells inside the body to use the potential of stem cells. They can be used for surgery, like implants, occlusion, and I will. And as well for tissue regeneration. I will describe some of these in the future, next slides. So like for targeted therapy, the microbots can be used for localized delivery. Usually at the moment we use the circulatory system to deliver medicine, so it affects all the cells, even healthy cells. It has side effects, but with highly localized delivery of medicine, so we can just affect those cells that we want. So it should have less side effects. They can be used in cancer therapy, delivery of medicine, delivery of drug-coated nanoparticles, or some already developed applications of these microbots. They can deliver heat locally to the cells. So in hyperthermia, we use the help of heat. So we expose body to a slightly higher temperature, like 40 to 44 degrees, for extended periods of time to improve the effectiveness of other therapies like brachytherapy. So we use hyperthermia. We can use the delivery of heat inside the body for thermoablation if we want to remove some, undesired tissues or fat, so they can be used for thermoablation. So we can raise the tissue temperature to the point of cell death, which is greater than 50 degrees. So if we can move the microbe inside the body and use the local heat to just make the cell die and remove those undesired tissues. And we can, there are several approaches. We can hit the microbots using high frequency magnetic materials. We can induce current in a microcoil, or use resonating magnetic structure to generate heat inside the microbot and to the area which is microbot close to that. So there are also brachytherapy, these applications of microbots. So a radiation source can be moved into the human body using the help of microbot and placed inside or next to the area requiring treatment. These therapies can be used in cancer therapy, different cancer therapies, and coronary or vascular applications. We also can use microrobots for delivery of stem cells inside the body and generate use for regeneration of tissues, generating organs using the stem cells. So the microbots can carry stem cells inside the body. They can be used as monitoring. So these smart pills, they have camera, they have sensors, they can be actuated using a magnetic field from outside. So they have a wireless capsule and the receiver, and they can be used for imaging or measurement of several parameters. They have sensors, and they can be removed from the body in a natural way. Sensing. So we can use microbots for sensing. So this is an oxygen sensor, an idea of an oxygen sensor for the use in eye, so they can have again receiver and send and receiver functions to send and receive signals and measure continuously monitor the parameters like this oxygen sensor. We can use microrobots to extract some tissues from the bodies, like a tissue sample from the body, and move to the outside for examinations, or they can be also combined with remote sensing to do in vivo functions. And they can be used, the microbot can be used as scaffolds, so they can, I mean, the structures, we can make 3D structures which is close to the shape of the organs that we want, and the cells grow inside and proliferate inside these scaffold to make new organs. We can use microbots in occlusion. So sometimes we want to use stents to keep the like a vessel open, but sometimes we want to close or block a blood vessel that nourishes, like a tumor. So these microbots can be used in occlusion applications. But when we talk about application in the body, let's say where in the body. So first, we want to look at eye. So I know there are several diseases like AMD, age-related macular degeneration. So, and several other, age-related disease for eye. These eye surgeries usually require phenomenal dexterity of the surgeon. Precision positioning is in the scale of tens of microns. Forces are out of range of human perception threshold, so they are usually in the micronewton, in the scale of micronewton to millinewton. So microbots in eye can have a wide range of applications. And in this video, we see a concept of using microbot inside the eye. The microbot is injected to the eye, and once there, it can be manipulated and actuated using those electromagnetic coils from the outside, and it can move. It can deliver medicine inside the eye or do surgery, and it can be removed from the eye from this same method we inject. So using the same method, we inject the microbot inside the eye. The microbot we can use in eye. So this is a developed microbot by ETH group, Professor Nelson, Bradley Nelson in the ETH. The size is around, the length is 2.5 millimeter. But the smaller size microbots can be also developed. So the microbot is fabricated using electroforming technology from a cobalt nickel, which has the magnetic, which can be actuated using magnetic fields. So it's and it can be coated by by gold or polypyrrole. So the coating is for non-toxicity, so it's biocompatible material, and it fits in a 23G needle, so it can be injected inside the eye. So here we have a white rabbit. So in a clinical trial of this microbot, so in the video, you see that the microbot is injected inside the eye and can be actuated from the outside using electromagnetic coils. So it can be moved around and do surgery or drug delivery inside the eye. So what we have used here is using a camera to have a view of the macro and control of the microbot. So the feedback in this case is from the cameras. So visually we could manipulate, actuate the microbot and track the microbot. Here it's another trial, but it's the human eye, so of a donor. So it's a 76 years old donor. So the microbot could be actuated and manipulated inside the eye of 76 and 75 years old donors. But in the case of a 36 years old donor, so it was so elastic, so the microbot jumped back to its position when it's actuated. And this is a clinical version of the actuation system. So inside there are 8 electromagnetic coils that occur inside the electromagnetic coil are changed to control the rotation and the motion of the microbot. So but there are also other applications. Just want to show you this video, like in cardiac application or cardiovascular system, we can use a microbot. So here we have got a catheter steering. So several groups are working on catheter steering for biomedical applications. There are huge electromagnetic fields which can surround the patient and apply magnetic field, like what we have MRI systems. The catheter is so flexible and can be manipulated, and it has the magnet inside, so it can be manipulated using the magnetic field, and it has the ability to generate heat for using thermoablations. Okay, so I want to talk about my a bit more about my research. So in 2011, we developed a ciliary microbot. We inspired by this guy in Paramecium. We developed a Helical Microbot. It has 2 rows of cilia in each side, so they move, but they don't beat in a symmetric motion. So it can mimic the cilia beating in nature. So we proved that artificial cilia beating can mimic their natural counterparts using this actuation force, and we calculated the propulsive force and propulsive velocity of the microbot. In another paper, we showed that using partial magnetization of the cilia, we can induce instability inside the cilia to generate, to make them both when they during the recovery stroke. So using this partial magnetization, we could make a microbot, a ciliary microbot with higher efficiency. Later, DGIST group, they fabricated the the ciliary microbot, and they manipulated the microbot to show that it can have motion. And we use usually magnetic actuation for the microbot. The magnetic field can be used to align the microbot in the direction that we want, and we can use magnetic force, which is related to magnetic gradients, to manipulate and actuate the microbot inside the fluid. So we see here we have a microbot aligned with the magnetic field, but the gradients show that the motion, it can move along those lines in different directions. So there, we have used the magnetic actuation formulation to derive the currents inside the core to find the magnetic field and magnetic gradients of an electromagnetic core. So the electromagnetic core system was a mini-mag with 8 relatively small sizes, so it could generate like 50 millitesla magnetic field, which is acceptable for, which is reasonable for actuation of microbots. And we could analytically derive the equations and find the magnetic field and magnetic gradients of the electromagnetic coils to control the microbot. So we could find, we could use this we developed a program, and we could use the program for control of a microbot, simulate the control of a microbot. And also I have used an algorithm, time delay estimation algorithm, to control the microbot. So precise control under uncertainties is necessary because we want to reach a target inside the human body, the microbot. We want to minimize health risks from the microbot during in vivo operations and ensure the goal is reached. So for this, we need a precise control of microbot. And but there are uncertainties in dynamic of microbots. So we usually need to measure the microbot weight, but it has some errors. So there are uncertainties in microbot weight. We have uncertainties in drag forces, how you can evaluate the hydrodynamic drag forces. And there are some other unknown forces as well. So van der Waals electrostatic forces or contact forces, these are all unknowns. And we have also nonlinearities with the magnetic actuation. So the problem is how to control a magnetic microbot under these uncertainties. So we developed the equation of motion of the microbot. So in the equation of motion, so we have got buoyancy force, gravity force, drag force, and the magnetic force. And there are also some other unknown forces in the equation. So we use time delay estimation, which uses the previous time step information of the system value to estimate the current value. So to control the microbot. So for variable that we don't know at the moment, we use the previous time information, and we could consider all the unknowns and uncertainties within a parameter, just we use time delay to estimate that from the previous step information. So with this algorithm, systems with nonlinearity and uncertainties can be properly controlled with a straightforward gain. So gain design also is much easier than what we have in PID control, and it can be easily implemented in time delay estimation. And this slide shows the algorithm. So we have got two gains here that we can design to get a desired aerodynamics, and we use M0 to tune the controller response. So we have three parameters to design the controller, and we implemented this system. This shows an experimental setup. So we have got two cameras from two sides, and with the lenses, and as well we have got the electromagnetic system, the magnetic actuation system. The microbot is inside this container. So the fluid we used here is silicone oil with a dynamic viscosity of 1 Pascal second, and we use the camera speed of 60 Hertz, so it's quite low speed for the camera. So even with this, at this camera speed, so we could control the microbot. The microbot was 500 micrometer in diameter and 1000 micrometer long. So we could control the microbot and to reach a step input, so to follow a step input to reach the point that we assign the microbot to move. So these are the graphs shows the position of microbot could follow the input, and so these are the experiments. So you see here we have got the characteristics or performance parameters of the control. So the controller was so fast. We have got a large overshoot, which is due to the nonlinearities in magnetic actuation, and as well a low camera speed. But when we could use like 100 Hertz camera for the camera speed, we could reduce this overshoot to 40%, 35%. You see in this video the control of the microbot using time delay estimation control. So then it shows the vertical, so it can move on a trajectory or between several points. So and the accuracy of the control is within 50 microns of the point. In another project, we developed 3D porous microbots, so these scaffolds. So we used 3D lithography method to develop these, with a length of 100 to 150 micrometers. So you see we have got very neat, structure, 3D structures at that scale, cylindrical, and we could manipulate these. Sorry, just try to. Okay, so we could manipulate using magnetic actuation. The cylindrical, you see here, the cylindrical, so we could align the magnetic microbot with an external magnetic field and use magnetic force to actuate it. This one, the microbot rotates, and we could apply force as well to navigate it. This shows the motion of two microbots together. So the magnetic field applies on both of them, and they have a simultaneous motion. And in the last video, you see the control, the PID control of the microbot. So you could control the microbot to achieve reaching those points, positions that we previously defined for motion. And these are graphs which show the magnetic force and magnetic field gradient applied on cylindrical and hexagon microbots, those scaffolds, and the velocity. So the velocity of the cylindrical microbot was higher than the hexagonal. That was because of the friction forces and drag forces was higher in the case of a hexahedron. So we could as well culture cells inside the microbot. So the microbots are made of SU8, but they are coated. They have been coated by a nickel layer and as well a titanium layer. So we could use nickel layer for the magnetic actuation and titanium for the biocompatibility effect. So you see here in this figure that the cells could grow inside the microbots, and it shows that the microbot has not been toxic to the cells. And we could publish this in advanced materials, and it made its way to the front cover of the journal as well. And that's also pictures of the microbot cells inside the microbots taken by confocal microscope. And in another project, I have worked on bio-inspired micro nanorobotic control. So there are different ways that microorganisms or bacteria use for direction control. So we can use the same method. One is running and tumble. So the helical flagella, they rotate, but when they stop rotating, there will be a tumbling for the microbot for the microorganism, and it can change its direction. We can use run, reverse, and flick for the microorganism. The microorganisms use run, reverse, and flick for the direction change. They can use helical path swimming. So in the case of helical path swimmer, they change the rotational velocity, so they can change the helical path configuration, and then it gave them the direction control or the direction change. And they can also use speed modulation. I've worked on these different strategies of microorganisms, bacteria, to develop new ideas for change the direction control of micro nanorobots. So still we have got several challenges for the microbots. So first one is fabrication. So we haven't got a motor like we have a molecular motor in the case of microorganisms. So if we could make a motor like what we have got in microorganisms, that would be perfect. So fabrication is still a challenge. New materials, using degradable materials for the microbot. How we can power and actuate a microbot. So the dominant actuation method now is magnetic actuation, but we need to think about other ways as well, functionalization. So microbots, they up to now, they are limited to just propulsion and motion. So they don't have a they don't have a function at the moment. So usually, so I mean, there are cases to prove that some catch and release or some surgery, but still there are many room to work. And control clinical trials and hybrid microrobotic system, these are challenges that we can work in the microrobotics and nanorobotics field. So hybrid microbot means that we can use the microbots with the bio microorganisms together. I would like to thank Professor Bradley Nelson from ETH Zurich. He shared some videos of his work with me. And thank you for your attendance, and I'm happy to answer your questions.
Thank you very much, Ali. It's been quite an interesting topic for me as well. It's quite new to me and quite enlightening, actually, what happens in the micro world, let's say. We have one question here, if you may answer. How big is the imaging micro robot that you showed to us? You know, the camera pill inserted into the eye.
Yeah. Yeah, that's the microbot. The length is 2.5 millimeter, but the diameter is smaller, like 350 micrometer. So, but we can see using those cameras. So we can, I mean, a lens. We can see even a smaller microbots, like 500. Or a small, like 300 long microbots.
Okay. I mean, yes, they're considerably small, but we are still a bit concerned about how would you then recover them from the body?
Yes, yeah, that's a good question. So, in the case of like application in eye, so they can be removed in the same way they are injected into the eye. But there are some work that they work on degradable materials, so they can dissolve after their application. So these are, still the researchers are working on, but like in catheter application, so they can remove the catheter. But in the case of microbots, still it's a challenge how to remove. Yeah.
Okay. Also about the activation force. I mean, you mentioned the magnetic field, but is there any other ways to give motion to the microrobots? It's
Yes.
just magnetic field at the minute.
Yeah, at the minute, maybe that's the most dominant approach, because you can transfer a high amount of power using magnetic field. It's safe. It has proved to be safe because we have used the MRI system for a long time, and the systems are also available, so we can use magnetic electromagnetic cores or even MRI systems. So mostly now is and it's wireless, right? So mostly is about magnetic actuation now.
Excellent. There's another question about the imaging, actually. What sort of images do you capture? Any use of infrared, for example? Is there anything different?
Yeah, there are several approaches they used in literature for for tracking the microbiome. So some researchers have used ultrasound images. Some researchers use, like in Canada, Professor Martel, I think, if I remember well. So they have used MRI system, MRI imaging. So that's also a good question. So there are different approaches that we can use, but in the case of eye, maybe the best way is to use visual, tracking.
Okay, excellent. I've got some questions here about the safety again. Maybe I should rephrase this a little bit. One thing about this is, can we actually maybe provide microrobots like within tap water system to a mass population for other health benefits? Do you foresee any applications like this?
You mean have the microbot inside the tap water?
Yes, something like that. Yes. I mean, rather than manipulating a microbot to do a specific task, maybe deliver some microbots with some predefined functions.
Well, uh, so that in the case of eating or drinking, so the microbots maybe your concern is about safety. They wouldn't have any they wouldn't make any safety issues. I would say if they you eat or drink them. So because the size is so small, even we talked about the smart pills. Okay, so they can be actuated from the outside, but they can be also removed from the body in a natural way. So I don't think there would be any harm or hazard from the those microbots by drinking them also.
Okay.
Yeah.
Let me read another question here. Is it possible for microrobots to change the structure of things like the DNA? Is there a problem with the scale?
Well, mm, uh, with the scale, so the microbot can affect, the cells. So, but the, if they can change the DNA or the DNA structure, Mm, so how we can change that? That's a good question. Maybe I don't have the answer for it now. So, but how we can change the DNA structure of cells using a physical or mechanical, intervention.
Okay.
Yeah.
I mean, when you think about robots or any other advanced technology, you sort of think about military as well. Do you foresee any misuse in the military or terrorist activities about these microrobots? Maybe a
Yeah,
bit
there might be.
controversial question.
you know, yeah, risks from but these microbots that we are working are generally used for biomedical applications, and they should be used in lab space with the supervision of medical doctors. So yes, and they are not like because there are like quadcopters, so they can be controlled. But these microbots, they don't have a controller inside, so the controller is outside. Okay, so maybe less risk compared to those, flying UAVs. Yeah.
Okay. One question. I mean, we have seen a rabbit as a patient there. You mentioned it's been tried on a donated eye of an elderly patient as well.
Yeah.
Has it ever been tested on a living human?
No, no, no. Because clinical trials is a bit difficult. So those in the eye of the donors, so donated by the dead people. So those have been done in Switzerland. So in Switzerland, it's a bit difficult. No, in the UK also, it's so difficult. So human trials, so they it's very difficult to manage and get the past the regulations. So not yet. So they are just in vivo within the eye of the donors.
I mean, is there any timeline in mind? Like it may take 10 years, 15 years, maybe 50 years to actually develop this technology to be used for humans then. Is there any timeline, do you think?
Yes, I would say within 10 years. So it was supposed to, for these clinical trials to be done by 2025, what we were talking about in ETH Zurich, in 2013 or 12. So at that time we were thinking that it can happen within the 10 years, but still there are steps to do. So there are challenges. I would say maybe 10 years, within 10 years. Yeah.
Excellent. Thank you very much for all the presentation and answering our questions. I think it's about 7 o'clock, so an end of time for us. I'd like to thank you again for all your contributions here, and I'd like to remind everybody as well to sign up to our other events as well, upcoming events. You have all the details on our IMechE Near You website. And thank you all very much for joining. Have a great day. Thank you.
Thank you.
Thank you.
Thank you. Bye.